0. Right. So last time we looked at the definition of elementary row operations. All right. So we had the following. Right. So we had let A be. Sorry about that. Okay, so we had an informal definition. So the informal definition was the following, that you can do three things. Okay, this is the informal definition. So you can do three things. So one is that you can multiply one row of A. Okay, so some fix some matrix A. Okay, so the first operation is you multiply one row of A by a non-zero scalar. Okay, so that's the first operation that one can do as an elementary row operation. The second one is you can replace the rth row of A by the rth row plus C times the sth row. Okay. Okay. Is that better? Still too small for you, but can't you look at it here? Isn't this one closer to you? What about others? What do others think? Can you guys read roughly? Okay, I'll just make a reference drawing for myself. So that's basically from here all the way to one. Okay, so that's roughly the size, just for me to know next time when I'm calibrating things. Okay, good. All right, so the third point is that, yeah, I'll hold the mic because the clip doesn't work, but I guess the audio is good now, right? Perfect. Yeah, thank you for telling me. All right. The third point is that, of course, you can interchange the rows, right? So you can interchange two rows. Okay. Okay. So that is just the definition. Okay. So and then why are we trying to do all of this? So an elementary row operation is just a special type of function, right, that associates with each m cross n matrix another m cross n matrix, right? So an elementary row operation is a map, basically, okay, that associates an m cross n matrix A with another m cross n matrix that we call E over here, right? So that's the elementary operation. Is a map E, right? That does this. Is that okay? Or if you have a question, you have to speak up because I don't. Yeah, just go ahead. Yeah, intuitive. Okay. You're not able to read it. Do you want to maybe come forward, because I think most of the people at the back can. You guys can, right? On the whole, you can read at the back. Okay. Can you come forward? Yeah, there's lots of space here. Okay. So this is fine. Okay. Can I scroll? Is it okay? All right. So so one can define it a bit more formally. So I'm going to be a little bit sloppy here, but you'll have the full notes with you, so you can look at it over there. But the formal definition would be as follows. Okay. So we'll say that the first kind. So these are elementary row operations.
One on the top left, the board.
Story, yeah. It's just, yeah, sorry about my handwriting. It's just like, this is not formal things. I'm just writing it so that you know what the narrative is. And there's like definition and other things to tell you where it's formal. Okay. So story is like informal stuff, just so you can, you know, sort of keep a higher level picture in mind. Okay. Right. So, okay. So elementary row operation. So, right, it's a map. So, okay. So let me just write it. So let A be M cross N matrices as above. And let E be an arbitrary function of the form above, right, that we mentioned. Then E must satisfy the following. Okay. Oh, shoot. Okay. Who was in charge? Or they're still writing? Okay. Oh man, my writing is so bad. It's a map E. So an elementary row operation is a map E that associates an M cross N matrix A with another M cross N matrix E of. Yeah, it's just the name of the variable. Yeah, it's just a map E. Yeah, it's like, you know, a human X. It's just that. Of the form above. Oh, right. So okay. So this is fine. And right. So right. So what is this map? So one can write this map a little bit more formally, right? So okay. So you fix some indices R and S and scalar C. Okay, that's not zero. So what is the map? The map is the following. So E of A ij is A ij for all I different from R. Okay, and it becomes C of O I equals R. Is that good? It's just formally writing down. Yeah, this is a bit too zoomed in for me. I have to keep zooming out. Okay. All right. Because that's the first point. The second point is,
Would you go back up?
yeah, I guess I'll have to keep the font slightly small. Otherwise, I think I'll have a bit of.
Would we receive the notes later?
Yeah. And this you already have actually on the thing. Yeah, I don't know what the best solution is. Okay, so the notes will be made available. So maybe try to write it in more shorthand, right? So that like you just write down whatever your thoughts are, and then the actual notes will anyway. Yeah, is that reasonable?
Yeah.
Okay. Great. Okay, so then the second point is that E of. Okay, so the second point was what? The second point was that you're going to swap out. Sorry, you're going to, when the index I equals is not equal to R, you're doing nothing, right? And when the index I equals R, what you're going to do is you're going to replace it with the rth row, like you keep the same thing, right? Plus some scalar times ASJ, right? Which is the sth row. So J is just indexing the entry of the column, right? The second part. And then the last part is, of course, that you're going to swap two rows. Let's do that. The third one is E of Aij is going to be unchanged when I, oh, sorry, X. Yeah, we have to assign a new person. Can you watch the board? What's your name? Ashwin. Like that? Yes. Okay. So you're doing the board now. Okay. The audio is fine, right? You can hear me at the back. Okay. Great. So Aij, So when I is neither equal to R nor equal to S, and yeah, okay, so this one I have to define more carefully. So E of A Rj is going to be A of Sj, and E of A Sj has to be the same as A of Rj. Right, so this is just getting you familiar with like writing indices and all these things. So this part is just capturing what we already had in the beginning, right? So we said here these are three operations, right? Oh, where are they? Oh yeah, here. So these were the three operations, right? You can multiply by a scalar, you can swap, and then you can keep the row plus add c times some scalar, right? So I'm just writing the same thing again, but with more formally, right? So here you're keeping the same, you're just, other than the rth row, everything remains the same, and the rth row is scaled by c, right? Here you're keeping everything the same except the rth row. You add c times the sth row, right? And the last one, you're just swapping the rows. So if the indices are neither R or nor S, then you keep the matrix unchanged. And if R and S are involved, then you swap them, right? Is that okay? Okay, brilliant. So let's continue now. Okay.
We go back onto this.
I mean, if you're not able to fully write it, it's still relatively okay. Okay, don't fret too much. If there's something which is unclear, you can ask. But for the notes, yeah, I think, yeah, I think try to optimize this not for making notes, but more for making sure you're following. That's like if you have to interrupt me, do it because you cannot follow. Notes, you'll get the copy. All right. So
Are you adding this?
yeah, yeah. Both those things are there. Like, there's like the full notes that I typed to from which I'm presenting and what we discussed in class. You'll have both of them. Okay. But it is still good to take notes to the extent that you can for your own understanding. But okay, right. So let's continue then. Right. So now in defining E, it is not really important how many columns of A we are considering. It largely depends on the number of rows, right? Because that's how these are operations on rows. Okay. So let me quickly write this. In defining the map E of A, we care about the number of rows and not really about the number of columns. Okay. So therefore, we are going to basically consider when we so when we speak of it, so when we speak of E, we consider all the class of all M row matrices. Over F. Okay. All right. The next point is why these specific operations, right? We could have considered any kind of operation. Why are we specifically looking at these operations? Why these operations? And it turns out that intuitively, after applying E on a matrix M or a matrix A to obtain E of A, right, one can recover the matrix A by performing a similar operation.
When we speak of E, we consider the class of all.
Where did I write it? In the class of all M row matrices. Yeah, sorry. Thank you. Thank you for asking. My handwriting can be a little bit bad because I'm trying to write very quickly so as to not waste time. So yeah, if something's unclear, thanks for asking. Any other questions?
Why recover is the better for you mean by that you saying that's by anything for this operation?
Yeah, we're sort of thinking in terms of linear combination. This is just the intuition. It'll become formal in a second, but the idea is that you can apply a similar operation and get back to it.
The still operation comes the first operation, then I can second operation to go back. So originally it takes on like the time of the first operation.
Wait for the theorem. Okay. It's coming in the theorem state.
So yes. Who was F particular minus one?
F was the field from the first section. So we're thinking of subfields of the complex field. That's if you have any questions, feel free to directly ask. Don't have to check with your
Columns.
Must be columns, yeah. Where are we looking at? The class of M road matrices over F. Oh, the M is missing. Yeah, the number of columns here. Right, yeah, you can just say columns. Oh, but it's not even usable. Okay. All right. So let's continue. Okay, so theorem 2. Theorem 2 is going to say the following. So let me make more space for you here. Right. So theorem 2 says the following. So it says to each elementary row operation E that correspond an elementary row operation E1 of the same type. Actually, maybe I should underline step of the same type as E, such that E1 of E acting on A is the same as E acting on E1 of A for all A. Okay. So in other words, the inverse operation of an elementary row operation exists, and it is an elementary row operation of the same type. Okay, is the statement clear? Okay, so all we're saying is that once you've applied an elementary row operation, right, which is what you were asking, if you apply it again, you will essentially return to, well, not the same operation, but the same type of operation. Then you can go back to where you started. Yeah.
How are we defining the type of operations?
So we defined three, right? The three types of operations. So it's the same. Yeah. Exactly. Okay. Any questions for the statement?
It's the same as saying that we have variations for the statements.
It probably should. I think so, yeah. Because you're able to go back, then it should probably, yeah. Yeah, as long as the scalar is non-zero, I think, yeah, that's probably correct. Yeah. Okay. Any other questions?
Necessarily, first, if you are returning back to A, it's just saying that the like applying geo and apogee of the same thing would be equal.
Yeah, maybe did I say the statement wrong? Let me check. Okay, so it's saying that to each operation there exists an elementary operation of the same type. Yeah, let's look at the proof actually. I think this will become clear. It's probably in the following statement. Yeah, it's not really saying anything about the inverse. Yeah, so maybe I said it wrong. Give me a second. Operation there exists an operation E1 of the same type as E.
So in textbook it says that it's equal to A.
Yeah, did I write it wrong? So there's also an equal to A, you're saying? Okay, that's what I remember now. Okay, let's look at the proof. Okay, just let's not take other people's word for it. Okay, even though it's the textbook, I'm just saying like that's the spirit of math. Like, you actually try to check.
It's the inverse operation have to come back to.
Yeah, but that's the specific wording. But in the formal statement, I messed up. I think so. That's why the person called it. Thank you. Okay, so let's look at the proof. Right. So the proof is the following. Okay. Yeah. So were there any more questions about the statement?
Even the inverse or is it just any specific type and still the part which you don't prepare?
So I said,
But if it inverse or the part it would not be valid for any one of us. Yes, but
uh, I'm not sure I follow. So you're saying that so this statement is true, yes, and you're saying
even if the inverse then you will add an equal to it.
yeah, we'll find out. Yeah, we will look at the proof and we'll see whether we get the inverse or not. But yeah, it likely should, right? Because it says in other words. So we'll see. Okay, right. So we do the proof separately. And this is actually kind of very, very trivial. Once you look at the definition, it's just saying like if you're multiplying by a scalar, you can multiply by the inverse of the scalar. If you're adding two rows by some constant, you can basically add, subtract with some appropriate constants. So that's all that it's doing. But let's look at it. Okay, so we do the proof for each type. For each type separately. Oh shoot, you cannot see it. For each type separately. Okay, so for the first type, so suppose E is the operation that multiplies the rth row of a matrix. Oh yeah, please take a minute and turn off your notifications. I will also do that because I forgot. Okay, great. So great. So suppose E is the operation where you're multiplying the rth row of a matrix by some scalar. Yes, by a non-zero scalar C. Okay, and clearly E1 can be taken to be okay. What can be taken to match the? So we want to match this, right? So we want to say E1 of yeah. Let's just ask for the inverse. So let's say E1 of E of A is the same as A. So suppose this is what we want. This is what we want. How do you choose E1 given this? Exactly. Okay, so it's completely trivial. There's nothing very complicated here. So you can take E1 to be the operation that multiplies the rth row with 1 by C, right? And so this is why we needed the C to be non-zero, right? Otherwise you cannot invert. Right? That's the first point. Right. Now let's look at the second point. The second one is the most complicated one. Here we say that suppose E is the operation that that replaces row R by row R plus C times row S. Okay, and S is different from R. Okay, so now clearly one can take E1 to be such that, or actually not to be the operation that replaces row R by row R plus minus C times row S. Is that okay? Does it add up? No. Okay, fine. I'll erase it. Okay. Tell me, what should the answer be? Speak up. Who's speaking? I can't see. Can you raise your hand first? Yeah. Tell me.
Row R plus minus C times row S.
Row R plus minus C times row S. Okay. Fantastic. Yeah. And why we chose this is because, right, we want to preserve this, right? We want to say E1 of V of A is actually A. Thank you. Mhm. Yeah, there's a little bit of a problem with the sync. Yeah, it's row R plus minus C times row S. I don't know. Somehow the sync is not very good. Let me see. Clearly, one can. Oh, yeah, it's not copying everything. Like on my iPad, it shows, but on the screen, it doesn't for some reason. I'm sorry. I don't know what the best solution is. One can. What the hell? Yeah. Okay. I think I have to just choose a new notebook. I think once the notebook gets too big, it starts creating problems. Yeah, I'm sorry. There's going to be these technical snafus for a bit. Hopefully. Okay, let me see if I can get it on the iPad now. Great. Okay, so yeah, let's just stick to what we had. Unfortunately, it's not showing the new notebook when I created it. Oh, it did. Oh, no, that's the one I created. So yeah, so let's. This is very unstable. I'm sorry, I didn't know it's this unstable. Okay. Wait, where is the rest of the stuff I wrote? Yeah, I think I may have to change tact and just display the. Okay. So since this isn't working, what I'll do is, yeah, for now I'll switch to my notes directly, and then I'll just teach you from what I have directly written. Okay, I'll sort it out later. I'm sorry for the inconvenience. Okay. Right, so you can see this, right? Is this okay? You can read. Is it fine? Yeah. Okay. I'm sorry. This is not how I wanted to teach because this can get really fast. But let's see. Let's see. All right. So right. So this is what I was writing, right? That you can. So you can clearly take E1 to be this operation where you take rho R plus rho R plus. So you replace rho R with rho R plus minus C times rho S, right? And that will give you the inverse. This is fine. Right? Can you read at the back, everyone? Is it okay? All right. Okay. And then for the last operation is very straightforward, right? If you're interchanging rows R and S to get the whole matrix back, you do the same replacement again. So that's completely trivial. So for all three operations, we have the fact that this is actually equal to somebody who pointed this out. Thank you. So the statement is indeed that you can get the inverse. Is that okay? Any questions? Okay, let's move on. Yeah.
Would there be functions where E of EI and EI of E is not equal to E, but they're E?
Could there be functions? You can construct functions, yes, but for these specific functions, it's going to be the case that you can always find any one. But in general, you could potentially construct more functions. For instance, you could take E to just be the identity map, right? And it will, whether you apply E first or after, it doesn't matter.
It could just give us E back.
Yeah. I'm giving you a trivial example, but I'm saying one can construct that. But for this definition, you have to have like a non-trivial. Okay. Okay, so let's continue. Oh, right. Sorry. Actually, you should also remind me if somebody asks a question, remind me to repeat it because I don't think everyone can hear the question. So the question in that was just asked was that, is it possible to have some operation E1 that just satisfies the first equality, not the second? Right. And the immediate answer is like you can take E1 to just be identity, right? It does nothing. So if you apply it on A, it gives you A back. So obviously it satisfies the first equality, which can be trivially satisfied, but not the second. Is that all?
But we can have E of the same time.
You have to speak up, sorry. Okay.
We can have E of the same type, which will satisfy the first part as well.
Yeah, it's the same everything. He was asking if there are other operations that may still satisfy the first one.
Could be of different types, like three types. Since you told both that there could be different types, only then could the first part not be satisfied. That is even E of B is not equal. If they are of the same type, we guarantee.
Sure. Like, so the way we did the proof, it is true that the first part is going to be satisfied. We did it type by type. That is true. But you can, yeah, I was just giving an example of a situation where you might not return, like it's not an inverse. That is all I was saying. Yeah, nothing very deep. Yeah. Okay. All right, so let's continue. Okay. So now we use these operations to define another notion of equivalence between matrices. Okay. So we defined using ease, right? So let's define it a bit more formally. So A and B, if there are M cross N matrices over the field F, we say that B is rho equivalent to A if B can be obtained from A by a finite sequence of row operations. Okay. So if you have two matrices A and B, we will say that B is rho equivalent to A if starting from A, you apply a bunch of these E operations, right? Different kinds of E operations, and you obtain B. So then we'll say that B is rho equivalent to A. Just a definition. Is that it? Okay, it will slowly become clear why we are doing this. So let's make a few observations that one can verify using theorem 3. Okay, so each matrix is rho equivalent to itself. Right, and that's just the definition. So there's nothing much to do. Okay. Second part is that if rho is sorry, if B is rho equivalent to A, then A is rho equivalent to B, right? Does that make sense? Right? The reason is that if you have a sequence of operations that you are applying on A to obtain B, you can apply the inverse operations, right? Starting from A to obtain, they call the E1s, right? For the different sequence. Is that okay? And yeah, there are too many constraints. I can't hold the mic and type. Okay. So if something's unclear, ask me and I'll try to. Actually, let me see. Maybe if I write on OneNote, it shows up without too much of a lag. Let me check. Okay, so right, let's see if you can see what I'm writing. It doesn't show it. Yeah. Okay, yeah, let's just continue. Another option is I can actually just share my iPad directly. How is it so far? Is it okay to continue like this? Are you able to follow? Is it too fast? Is it okay? Without the pen? Is it okay? Okay, so let's just continue that. That's fine. Right. So if B is rho equivalent to A, then A is rho equivalent to B. So that's fine. And the third step is that if C is rho equivalent to B, right, which means that you can go from. Oh, someone's knocking. Can one of you please check? Right. So if C is rho equivalent to B and B is rho equivalent to A, then C is rho equivalent to A. Right. So what this is saying is that there are a bunch of operations that you can apply on B to get to C, and there are a bunch of operations, elementary row operations that you can apply on A to get to B. Then you can apply a bunch of operations starting directly from A to obtain C. Right? It's nothing very complicated. And this is basically the criteria for an equivalence relation. So if you don't know what that is, it's okay. It's basically just these three conditions that the object has to be equivalent to itself. If A is equivalent to B, then B has to be equivalent to A. And the third point is that if C is equivalent to B and B is equivalent to C to A, then A and C are equal. Those are the three conditions. Okay. Alrighty. Great. So now we have if A and B are row equivalent M cross N matrices, then, and this is like the fun part, the homogeneous systems of linear equations AX equals 0 and BX equal to 0 have exactly the same solutions. Okay. So does anyone immediately see the proof of this theorem? Okay, so you see the proof already, okay.
Basically, every row operation is based on a linear combination of the system. So it will always have the same solution if you are applying a row operation. And if we perform it multiple times, we will eventually reach the problem.
Right. So that is roughly the idea that if you have a bunch of equations, right, and they're all satisfied, if you take a linear combination of these, then that will also be satisfied, right, by the same initial solution. So we're going to use that in proof. Yeah, but that is the right intuition. Okay. Right. So let's try to do the proof a bit more carefully and to formalize this idea. So suppose that we go from A to B by a finite sequence of elementary row operations. Okay, so you're starting from A0, and suppose you go through this entire sequence to reach B. Note that it is enough to prove that the system A sub j x equal to 0 and A sub j x plus, sorry, a sub j plus 1 times x equal to 0. So these two systems of equations, they have the same solution. Okay. So that is enough, because then we can argue that for each arrow, the set of solutions stays the same. And so therefore the solution from A to B would be the same. Exactly. Exactly. So the point here is that you're trying to formalize these things, and we'll see it ends up being quite powerful, in the end. But that is exactly so the things you've been doing for like forever is what we're formalizing here. Okay, so you just add, subtract, and then you find some way to do it. The difference is now we'll do it systematically. We'll come up with like an algorithmic way of thinking about these things, and find properties of these things. Okay. Right. So the first step is clear, right? The observation is fine that if we can show that for each arrow, the set of solutions stays the same, then we're done. Right. Okay. And how do you establish that the set of solutions stays the same for each arrow? So suppose that C is obtained from D using a single elementary operation. Okay. So C and D are like, they're basically just sitting as these two matrices, right? AJ and A sub J plus 1. So I'm just being a little lazy and calling them C and D. Now, it doesn't matter which three types of elementary row operation that you used. It is clear that each equation in this system is just a linear combination of equations in AX, right? Which is what somebody had just pointed out. I should probably write. Yeah, okay. So I should have written. I messed up my variables. It should have been C and D. So let's correct that. Okay. And furthermore, since the inverse of an elementary row operation is also an elementary row operation, each equation in dx will also be a linear combination of the equations in bx. Right? Huh? Did I mess up? Oh shoot! Yeah, it should be C. Yeah, thank you. Yes, thank you. Is this correct? Did I mess up? No. Okay, good. So therefore, the two systems are equivalent, and by theorem 1, we'll have the same solution. Okay, so remember last time we proved this theorem, it said that if two systems of equations are equivalent, right, which are basically that they are connected by these elementary row operations, then the set of solutions is the same. Now, all we have to do was to establish that they are equivalent, and that's it, right? And then we use this transitivity property, right? This property here, that if C is equivalent to B, B is equivalent to A, then C is equivalent to. So then you can run the whole thing. Well, that's also another way of doing it. Here we are just arguing that the set of solutions stays the same. So that's also fine. Okay. Any questions about the proof? Okay, so let's continue. Right. So now let us look at how one might use these elementary row operations to potentially solve a homogeneous system of linear equations. So this is stuff that you've done multiple times. In maybe not with matrices, but by yourselves, right? So I'll not necessarily go through this. I think maybe we can skip it. But very, very briefly, the idea is that intuitively what you're trying to do is you're trying to remove, you're trying to make certain elements zero, right? So for example, here I'm trying to make this column all zero except at one place. Right, so I'm applying linear combinations of this row to the first and this row to the second in order to get this column. Once this column is settled, then I try to remove the entries. So I normalize the -2, right? Get it to be 1, half, whatever. And then I use this one to remove these two entries, right? By applying the row operations and subtracting them. Is it making sense? It's either going to be too slow or too fast. It cannot just be okay. So it's probably too slow. Okay, good. So you basically apply these operations, and in the end, you will end up with a matrix by applying those elementary row operations, which has exactly this form. So it has a bunch of ones and all other zeros, and then there would be potentially some extra column with extra values. Okay? And in terms of matrices, right? In terms of equations, you basically simplified this equation, right, which is what somebody was saying earlier, into this set where you have a bunch of variables, and then the last variable x4 is appearing with a bunch of coefficients. And the point is you can choose whatever value you want for x4, and you will obtain a solution, because you just take x3 to be whatever this object is in terms of x4. Okay, so in particular, if you take x4 to be C, then you know that this object is going to be a solution simply by solving this. Is that okay? Does it make sense? Yeah. Okay. Trivial, but is it good to mark some? Okay. So here's another example where yeah, let's not worry too much. Okay, so let's not worry about the details, but what is nice is that, this example has like a bunch of complex entries and things, and so you might think that it's a bit more complicated, but it turns out to just be this diagonal thing right here. And if you have one somewhere, then it obviously cannot become zero except when the variables themselves are zero, right? Because this is at the end of which is going to be the same as x1 equals x2 equal to c. Right. Okay. All right. So now what we want to do is we saw, this is like intuitively what we want to do, but we can more formally write down what this this procedure is. And this eliminating of unknowns, right? So let's try to formalize this. Okay, so we say that a matrix R is row reduced if the following two conditions hold. The first is that the first non-zero entry that you get in a non-zero row has to be 1. Okay, this is what we were doing intuitively, right? So if you look at this matrix here, what we did was, or if you look at the one above here, right, what we are doing is we are taking the, whichever row we are taking, and we're ensuring that the first non-zero entry is 1, right? That is essentially intuitively the form we're trying to get. Why we're doing this is so that you can just immediately get the value of the variable. So x1 would be, or x3 would be that value, right? Is it making sense? Okay. So, so that is the first condition. And the second condition is that each column of R, which contains the leading non-zero entry of some row, has all its other entries equal to 0. Okay, which is also fine, right? So if you look at the condition here. So whenever you get the first non-zero element, the remaining elements in that column are 0, right? Okay, and the reason for doing this is so that we know that these variables are not interfering with anything else. Like, so these variables are, like, you can essentially say x1 equals something, and it will not depend on the previous variables. So like, if you look at this equation, right, so x1 is not going to depend on any of the other x's, except for the ones in the last column potentially, or the last set of columns. Okay, so that is the rationale behind why we are doing it. Trying to get rid of, basically making the variables as independent as we can. So we can solve them. Is that good? All right. Okay, so let's look at another example. So here, an example of a row reduced matrix. Okay, sorry, yeah. So that's the definition of a row reduced matrix. Okay, so those two conditions. The first non-zero entry has to be 1, and all entries along the column of that first non-zero entry have to be 0. Just two conditions. Okay. So let's look at an example of a row reduced matrix for a square matrix. Okay, and this essentially has to be identity, right? Because identity or permutations of identity, because it's an n product matrix. You can't, you will hit a non-zero entry. Of course, assuming that there are no zeros. Of course, if there are zeros, then this doesn't apply. But if all the rows are non-zero, then it has to be an identity if it's in the row reduced form, up to permutations. Okay. Right. So like I already argued, right, these matrices are already in the row reduced form. Okay, but let's look at some matrices that are not in the row reduced form, because that is also sort of important. So okay, so yeah, that's the annoying thing, because you can see the answers immediately. So I can't even ask you. Okay, let's try to hide the answer. Okay, so now in this first matrix, is it in? Okay, it already says it's not row reduced. Okay, why is it not row reduced? Somebody who hasn't answered it, raise your hand, and I'll ask. Nobody wants to raise their hands. Exactly. Right. So this the third column has a -1 entry, right? While the definition said that the first time a row gets a non-zero entry, that specific column has to have all other entries equal to 0, right? Okay. How about in the second example? Is this in the row reduced form? I mean, it's not, but why not? You can raise your hands if you want to. Exactly. Exactly. Is that okay? So sort of the idea should be clear. Okay. So let's move on. Right. So the theorem, theorem 4 says the following. It says that every m cross n matrix over the field F is row equivalent to a row reduced matrix. Okay. So what does the theorem say? This theorem is saying that you can start with an arbitrary matrix, okay, m cross an arbitrary matrix, and it will be row equivalent to some row reduced matrix. Row reduced matrix meaning the one that has the form that you described. Okay. So this is what you've been intuitively doing, right? Like when they give you a bunch of linear equations to solve, what you're trying to do is you're trying to get it into that nice form so you can solve it. And this theorem is saying that regardless of what system they give you, that form would always exist. You can always get to that form, and it would be equivalent. You can do it through these elementary operations. Is that okay? Is the statement clear? Yes, no, maybe. Okay, okay, good. Right. So the proof, so let's do the proof. So let A be an arbitrary m cross n matrix over F, like the theorem says, and we'll go row by row. Okay, so we'll do it for the first row. Right. So the first thing we check is the first row entirely zero? Okay, if the first row is entirely zero, then we essentially already satisfied the condition, right? Because the conditions were only for the first non-zero entry in the row. Okay. So we don't have to worry about it. So that is fine. If the first row has a non-zero entry, okay, we're going to let k be the index for which, so basically k is the smallest column for which the entry becomes non-zero. Okay, so a sub ik is non-zero. Now what we are going to do is we want to make this, okay, so let me keep it like this. Okay, so now what we want to do is we want to make this first non-zero entry into 1. Okay, so what elementary row operation do you think we can apply? Exactly. Is it okay? Take a minute to think about what row operation would you apply in order to make sure that this entry, after applying the row operation, becomes 1. Is it too easy? Is it too, I don't know, because anyone who hasn't answered yet, do you want to attempt answering the question? So what I'm asking is that you look at the first row, okay, and you find the first non-zero entry at the kth column. Okay? Now I'm asking what elementary row operation will you apply on this row or on this matrix such that this first non-zero element becomes 1. Exactly. Okay, so that's the first simple thing we're going to do. So we're going to multiply row 1 by A inverse of A1k. Right? Actually, I should write, should be 1. Okay. And then condition A is satisfied. Its condition A was that the first non-zero entry has to be 1. Right? Okay. Now we have to make sure that all the other entries in column K are 0. Right? That is the next thing we have to ensure. How do you do that? Well, you're going to add minus aik times row 1 into row I. Okay. So let's think about it for a minute. You're at the ith row. Okay. The kth column of the ith row is going to be a sub ik. Correct. And you want to remove this entry. You want to make it 0. Okay. And we know already from the previous operation that the first row has its kth column as 1. Right? So all we have to do is multiply it by minus of that entry and add to that ith row, and then it will disappear. Right? Okay. So that's the second step. And you can do it for every I. You can do it for every row. Okay, so now you're in the form where you have the first non-zero entry of the first row as 1, and all the other entries are in that column are 0. Does that make sense? Right. So let's think about it. So you have the first row at the kth column is 1, right? And now you want to remove, say, the ith row at the kth column has some value, say alpha. Okay. So to remove alpha, what you're going to do is you're going to apply an elementary row operation where you add to that row, the ith row, alpha times row 1. Sorry, minus alpha times row 1. Right? So it'll just be plus alpha minus alpha, and that'll disappear. And you can do this for every I. There's no problem. Is that okay? Does it help? Okay. Great. And okay, so let's go move on to row 2. So row 1 is done. So the first entry is 1, all the other entries are 0. For row 2, what we're going to do is we're going to start again with the observation that if all the elements are 0, then we have to do nothing, right? So we only worry when row 2 has some non-zero element. And again, you take the first we apply essentially the same operation. So you take the first non-zero element and you multiply by its inverse, right? And that will give you 1, like we did in the first row. That is fine. And one can apply exactly the same reasoning. So here it says like, okay, yeah, let's go through a bit more carefully. So suppose that the column at which you got the first non-zero entry for the second row was K prime. Okay, so last time it was K. So let's assume it's K prime. It is guaranteed that K prime cannot be equal to K. Right? Why can K prime not be equal to K? Exactly. Anyone else? But why can the why can K prime, which is the first non-zero entry of the second row, not be equal to K, which is the first non-zero entry in the first row? It's the index first, column, the index of the column. Can you raise your hand, please? Yeah. Exactly. Okay, so we made sure that in the first when we were analyzing row 1, we made sure that all the other entries in the column where you get the first non-zero entry for the first row, right? Those are 0. So therefore, it cannot be that K prime is 0, right? Because it's a non-zero entry. Is that okay? Okay. And then one can do exactly the same thing, right? That we did as before. So you take row 2, the first non-zero entry is 1. You can scale it and multiply it with all the other rows. And now, because already in the kth column, the entries, all the other entries are 0, when you add subtract, nothing will change. They will continue to stay. Okay, so that is the crucial observation, that once you fixed the kth column for row 1, doing subsequent operations will not change the fact that it's a valid column. Okay? And now you have a valid column for row 2. Okay, and then you can proceed. Is that okay? Okay, if it's not clear, you can go back and take a look. All these notes will be available. You can go through them at your pace. And yeah, okay, so that completes section 1.3. Okay, so now we look at section 1.4. If there is a gap between K dash and K, then there will be some multiple comments in between them. So it's not necessary that every element in row 1 even becomes every element in row 1 is not supposed to become 0, right? After 1, there can be some other elements. Yes, that can happen. But what we know is that, so basically you'll get a form like this for sure, right? You'll get a form of this nature. So at the end, like there could be extra columns that are non-zero, which we cannot handle. But at least for each row, whenever you have a non-zero entry, you can make sure that all the other, all other entries in that same column are 0. That much you can control. Okay, so the question was that you cannot do this process for essentially all entries. Okay, so obviously there would be non-zero entries that get left, which is okay. All we are saying is that the first non-zero entry has to be such that everything else in that column is 0. That's all we guarantee. Okay. Any other questions? Okay. So let's continue now. Right, so now we are on section 1.4 of the textbook. We're looking at row reduced echelon matrices. And here, what we've looked at so far is a system of linear equations and how to solve them, right? And in the previous section, we sort of gave a standard technique on how to obtain such solutions, right? So getting them into this nice form is basically allowing you to find the solution. Now what we're going to do is we're going to make it, we'll formalize, we'll add a few more conditions and make it a little bit nice for theoretical reasons. Okay, so let me just tell you what the definition is. So we already defined a row reduced matrix. Now we're going to define a row reduced echelon matrix. Okay. And what this basically is saying is that it is trying to make it diagonal like. That's basically what it's trying to do. So earlier it could be in whatever order, right? Like for example, when you saw this matrix, it could be in like whichever order, right? Like it doesn't have to be anything, but it's clear that you can commute it and make it diagonal like, right? Like you can get the second row to be the first. Basically, you can push the first row to the bottom, right? And then it'll become diagonal. So the definition is basically just trying to formalize this. That like what are the conditions that one would impose in order to ensure that it looks diagonal. So the first requirement is that it has to be a row reduced form. So this is fine. Now it says every row of R that has its entry 0 occurs below every row which has a non-zero entry. Okay, so if you have a row which has all entries 0, okay, those have to be at the very bottom of the matrix. That is the first requirement. Second thing is that if rows 1 to R are the non-zero rows of capital R, so suppose that you're indexing from 1 to R, the rows that are non-zero, then the leading non-zero entry of row I occurs in column Ki. Okay, sorry, there was an if. Okay, so this is nomenclature at this point. So okay, so we are going to look at these rows, and for the ith row, suppose that the first non-zero entry appears at K sub I. The column is K sub I. Okay, then what it is saying is that the columns have to be ordered. So if you're earlier, your column has to appear first, then in the second row, that column, third row. Basically just the order, making it diagonal. Okay, that's what it's saying. Okay. So here's another way of defining a row reduced matrix. So this is easier to understand, right? So it's saying that beyond a point, the matrix is going to be 0. At the beginning, it's going to be like identity. So delta ij, remember, who knows the definition of delta ij? This Kronecker delta symbol. Has anyone seen it before? No? Raise your hand. Okay. Exactly. So delta ij is basically just the following definition, right? It just says that. Give me a second. Okay. I'm gonna put it here for just a second so I can type. So here, delta ij is the same as basically this is 0 if I not equal to j. Delta ij is 1 if. Okay, so that's sort of the definition of this function. So it's basically just the identity matrix. It's saying any off diagonal element is 0 and diagonal elements are 1. Right. Okay. Right. So it's saying that the 0 entries have to be at the bottom, right? They're beyond this little r. The first block is just diagonal. It's just explicitly saying it, right? Because delta ij is the diagonal matrix. And then finally, it's saying that the ordering has to be correct, like the index order. That's it. Okay. All right. So now let's look at this example. No, it's not necessary. Yeah. So the thing is that when we are giving a definition, we have to consider, don't have to, here we are considering the most general matrix. And when you're considering the most general matrix, it is possible that the rows can be 0. So that's why we have to get in the definition. Okay. Right. So example 8 is saying what? So example 8 is saying that the identity matrix and the all zero matrix are row reduced echelon matrices. This is fine, right? This is just essentially by definition. We're not doing anything complicated. Yeah. Tell me, what are you discussing? Is something unclear? Can't you say it again?
So I guess no, that's
Oh, okay. You can also look at it on Teams if you want. Just a heads up. But okay. Any other questions? Okay. So let's continue. So theorem 5 is saying the following. So every M cross N matrix A. Oh shoot, I forgot. Oh, here's a non-trivial example. Okay, so this object yeah, this is also in the is it in the row reduced form? Probably. Yeah, because you cannot permute columns, right? So it looks like identity because you have to take it with a pinch of salt. It's not exactly identity. So this is a good example because it shows that you can have leading zeros, for example, right? Identity never has leading zeros. It never has a column which is zero, right? Also see that there's this entry that we are not able to do. Oh, this was an alternate definition for the same thing. Yeah. Okay, so this is a non-trivial example of something that is a row echelon form or a row reduced echelon. Okay. All right, let's continue. All right. So theorem 5 is saying the following. So it's saying that every M cross N matrix A is row equivalent to a row reduced echelon matrix. Okay, so earlier we got to the point where we said every M cross N matrix A is row equivalent to a row reduced matrix. Right? That's what we said in the previous theorem. Now we add this extra thing. Right? So this is the new step, this echelon part. And well, I mean, it's not hard, right? Okay. So first of all, we already know from theorem 4 that it's equivalent to a row reduced matrix. And it's not hard to see that a row reduced matrix is equivalent to a row echelon matrix because you just have to reorder the rows, right? So everything else is already done. Right? You just have to like make sure that all the zeros are at the end and all the columns, whenever we have a non-zero column, it has to appear first. So it's just a question of reordering this. And reordering we know already is a row elementary row operation. Okay. All right. So in examples 5 and 6, we saw how row-reduced matrices help in solving homogeneous systems of linear equations. So now what we're going to do is we're going to discuss those in this row-reduced echelon form, where R is in row-reduced echelon. Right. Okay. So what is the notation? So let 1 to R be the rows, the non-zero rows of capital R. And suppose that the leading non-zero entry of row I occurs in column K sub I. And let U1 to UN minus R denote the N minus R unknowns that are different from X sub K1 to X sub KR. Okay, so what this means is, let's be a little bit. Give me a second. I think I added some material and did not move this. So let's put it down. Okay, so here what we are saying is that you're going to have R rows, right, where there would be like a leading one, right? And there's a bunch of zeros afterwards. So corresponding to each one of these, there would be some x, right, when you multiply it. So those we are calling x sub k1 to x sub kr, right? And then the remaining variables, right, which have different coefficients, those we are calling uj1, or sorry, u sub j, where j goes from 1 to n minus r. Okay, so if you want to look at this example, for instance, it would help. Let me go back. Right. So, corresponding to each one of these, there is x, right? So it's row times column. So for every column, there would be some x, right? And for the last one, we are going to introduce a new variable called, we were calling it x4, right? So it was x1, x2, x3, x. The x4 is now what we're calling u1, u2, u3. And all these are what we're calling x's. It's just a matter of convention. That's it. Okay. So going back here, what we are saying is, oh, right? So this is what I'm writing, right? So because it's in row echelon form, you would only have one x, right? Because all the others are 0 at that point. Is it not clear? Maybe I should wait. I'll get the matrix. Give me a second. Let me copy this. It would help. All right. So okay, it's not quite in the row echelon form, but just pretend that this top row is at the bottom. Okay. So now in every equation that you write, right? So every equation would have only one x because I'm only labeling these the first three columns using x. The fourth column is labeled using y, using a u variable, right? So you have xk1, xk2, and so on, all the way to xkr, and plus some extra coefficients which would come from these extra columns. Okay, so that's what we're writing, and this is equal to 0 because we're trying to write because we're trying to write Rx equal to 0, right? That is, and R is this matrix over here. Okay. All right. Is this clear? Is the notation clear? If there are questions, ask me, okay? Because if something's unclear, ask me immediately because things built on top of each other, and then you'll get lost. Yeah. So what we're doing now is let's look at this more carefully. Right? It's saying that so the rows in the row echelon form, right? There are R rows that are non-zero, right? So how many rows are non-zero here? There are 3 non-zero rows, right? And pretend that this is like the first row is at the bottom, right? So it's in the row echelon form. Otherwise, it doesn't work. Okay. And then the leading non-zero entry of I of row I occurs in column ki, right? So for us, it would occur in the first column, second column, third column. So that's fine. So for each of these rows, we would introduce a new variable. So x1, x2, and x3. Okay. And then for the remaining columns, right? So there's 1, 2, 3 columns. There are more columns. For those, we would introduce u1 to however many you need to span all the columns. Okay. So now when you write down r times x equal to 0, this would basically correspond to this system of equations. So you would have xk1. So k1 you can think of as 1, right? So you would have x1, which is coming from this here. So it's row times column, right? So row times x1, yeah, maybe I can write 1, 2, x3. Right, so when you multiply here, you would have x1 times 0 times x2 times 0 times x3 times some coefficient times u1, right? For the next one, you would have 0 times x1, 1 times x2, 0 times x3 times u1 times this coefficient and so on. So that is all it's doing, it's just rewriting it in this form. Is it clear now? Yeah? Okay. All right. And all solutions to the system of equations Rx equal to 0 are obtained by assigning arbitrary values to these u's and then simply computing x1 to xk. Because they should be xk1, xk2, but doesn't matter. Basically, what you're doing is you can choose whatever u's you want, right? And once they are fixed, they immediately tell you what the x's should be, right? So it's just systematically saying that if you have a homogeneous system of equations and you construct the row echelon form, which we know you can, then you can read out the solution by essentially plugging in arbitrary values for u's and computing the x's. Is that clear? Okay, so it's just formalizing what you already know really well. Okay, it's just solving linear equations. That's it. But we're doing it a little bit more abstractly. Okay. So yeah, so here we are basically going through an example. So this was the matrix, right? The row echelon matrix that we had. So here K1, so the number of rows that are non-zero is, yeah, okay, let me ask you. Okay, how many non-zero rows are there? Oh shoot, it's time. Isn't it 1:05? The scheduled time. Okay, should next time somebody has to tell me. Okay, I'm sorry. Yeah. So let's maybe stop here. You can look at this example at home.